Well, we're almost there. Welcome back, everyone. We're just running the clock down. And it's official. Welcome back, folks. Looks like a small class, but we'll still get through it. And this is a hard one to attend. It's the last class right before going on spring break, which is well deserved. We got through exam two, and I'll be working on grading them starting on Friday. I hope to finish on Friday, but worst case, I'll be sending them back Sunday evening. Again, I hope to get them done as soon as possible, but it could go back as late as Sunday if I'm a little bit behind. Well, for what we're doing today, we're going to just continue on through chapter 19. We may finish it today, and if it does get finished, the due date will be April 1st, but we're not going to try to race through it, especially when we're all kind of tired after getting through the exam and it's right before the break. So we'll see where we end, and if we need to push the due date back further, we'll do so. Well, any questions at all, folks, before we get started today? Okay, well, let's begin, folks. We're looking into the central limit theorem for proportions so that we can extend pretty much everything that we did in chapter 17 and chapter 18 into the land of categorical data. So P is going to be the population's proportion of successes, where we're measuring a categorical variable with exactly two outcomes. A success is the part of the study that we're interested in, and a failure is just the other category. The sample statistic, p hat, is going to measure the proportion of successes in the sample. And then the central limit theorem for proportions tells us the sampling distribution of the statistic, p hat, will be approximately distributed normally. The center is the parameter, the true thing that we want to measure, the population's proportion of successes. And the standard deviation takes on this interesting, complicated structure right here, inherited from the binomial theorem. And putting this all together, here's the central limit theorem once again. We're just about ready to extend all of this into confidence intervals and then hypothesis tests. But before we get there, we need a standard error. So that's what our example 3 is going to be all about. Well, here's just the same formulas we're looking at, same definitions. P is the population's proportion of successes. So P would go here, here, and here in the central limit theorem. We take a sample of size n, find out the number of successes in the sample, and just a bit of a review from what we did on Thursday. We define a discrete random variable x to be the number of successes. And then we calculate p hat to be x, number of successes in the sample, divide by n. If we wanted a percentage, we'd multiply it by 100, put in a percent symbol. We're considering these as proportions, which is not a bad idea because all of our formulas have to be written as proportions, not percents. So what this gives us is a probability model for the statistic itself. In example 2, we showed how to use this directly in a somewhat realistic sort of scenario. But now we're turning back to honest inferential statistics. Any questions at all, folks, with the central limit theorem? Okay, so here's what we're going to do next. The moment we get our standard error, we're in business. We can jump right into the confidence interval procedure. So same kind of setting, we're going to assume we have a simple random sample of size n. The population has true proportion p of successes. And we want to know the sampling distribution of p hat. We know it's approximately distributed normal up here, and it has that particular standard deviation. But here's where we run into trouble. Our goal is to estimate p. And while it is true that p is approximately equal to p hat, we have the same exact comment that we've been making really since the first day of class. That estimate is useless until we can describe the error in making the estimate. So that's what the standard error is all about. We can describe the error if we bring in the standard deviation, describing how the data varies. But because P itself is an unknown parameter, the standard deviation here is also unknown. So this is what we do instead. We use this estimate right here. We can say, since P, this is the unknown, is approximately equal to a known value once we've taken the sample, recorded all the data. Once we have this approximation, we can just come up here and make approximation. The square root of P times 1 minus P divided by N itself is going to be approximately equal to the square root of, in place of where the unknown parameter is, put in the known statistic P hat, times 1 minus P hat divided by sample size N. So we have that estimate available to us, and that's the thing that we call the standard error. It's a brand new standard error. We had one in chapter 17, another one in chapter 18 that took on a very different structure. And so we often don't just say SE unless the context is ultra clear. We are usually a little bit more descriptive and say standard error of P hat. This is the new statistic we're measuring. This is going to be equal to, we say directly equals because we know we're using the approximation already. When we say standard error, it's P hat times 1 minus P hat divided by sample size N. So with this structure right here, we can now talk about what the confidence interval would be for the unknown parameter P. We can do better than just a 1-point estimate with P hat. We can put in an entire margin of error in that estimate now. Well, any questions at all, folks, with our brand new tool, this standard error here? Okay, and looking back at what we did in chapter 17, because the parallels are so strong, it's almost the same kind of thing. The only difference was it was a different normal distribution. It had two unknowns, an unknown parameter mu, the population mean, a second unknown parameter sigma, the population standard deviation. We had to estimate sigma right there, and so we said use the sample. S is the sample standard deviation. We plugged it in. That estimated the entire standard deviation here, and that was our standard error back in the land of quantitative data. The logic's the same, but the landscape's a little bit different. This is a one parameter family distribution here, yet we still go to the standard deviation, we make an approximation with the statistic, and pick up the standard error. So with that structure here, here's the entire method. Actually fits on one page, no scrolling. It's all here really. So if we want to estimate an unknown population proportion P of successes, we draw a random sample of size N, check 3 different conditions. Here, on condition number 1, we'll briefly comment. Either the data is going to tell us it was randomly sampled, it might be missing that information. If we have reason to doubt that it's a simple random sample or randomization at any point, we should mention that as well. But here again, we just briefly discuss what we know from the context of the problem. Condition 2, we can check directly. So we have to show the values here. NP hat times N times, and N times 1 minus P hat rather. So in order for the central limit theorem to be effective in this context of confidence intervals, notice that the counts are a little bit different. N times P hat is the number of successes in the sample, and N times 1 minus P hat is the number of failures in the sample, and they both have to exceed 15. And you might say, wait a minute, the central limit theorem said it was effective if it exceeds 10. So why are we going even higher? It's because we're making an estimate at the same time. This was already an estimate. It's an approximate sampling distribution. But if you don't know P and you're estimating it again with P hat, we have to go higher on the sample sizes. So the advice, which is pretty decent conservative advice in our textbook, is larger than 15 on both of these. And just for extra description here, this is number of successes in the sample. And likewise, the second one, because we have the complement rule, 1 minus p hat, this is number of failures in the sample. So on condition 1, again, we just make a brief comment. But on condition 2, a common mistake to make that could cost us some credit is we should say what these are to alert who is ever reading this that we know the exact number of successes, we know the exact number of failures. They both exceed 15, and if that's the case, we'll say the conditions are met. If one of these inequality fails, if say the number of failures is 14, then the large sample confidence interval for a proportion is not effective, and a lot of things could go wrong. If we say 95% confidence, the true confidence might be substantially lower, 93, 92%, for example. So let's say here, just for the sake of working out homework, be sure to state these counts on homework and exams. Once we get closer and closer to exam 3, that will be a helpful comment to recall. So that's 2 conditions. And the third condition, well, it says the population must be much larger than the sample. Reason for that is everything's based off the normal distribution, and that distribution can fail in a certain way. Here we have a simple random sample that's hopefully giving us independence, but independence on our observations can actually fail for this categorical data if we take a sample size too large, say more than 10%. Normal distribution becomes ineffective, and we need a whole different procedure to actually analyze our data. So the rule of thumb that's provided is that the population should be at least 10 times the size of the sample. Let me see if I can put in just a little bit of space here. That almost worked. Let me fix this. So this is something that's, again, not easy for us to check unless we do a whole lot of research, maybe demographics research, that kind of stuff, looking into the historical data. So this is something that we'll just briefly, that's supposed to be the letter B. Let me try again. Briefly comment on. If we have reason to doubt that this is true, we'll mention it when we give our conclusion. Well, if all 3 conditions are satisfied, then here's the method. We measure the number of successes in the sample, that's p hat. After that, we use a critical number, z star. It comes from the normal distribution, and this is the exact same method that was screenshotted in from chapter 14. So no t distribution on this one. We calculate the standard error p hat through the formula we see on the right, and we have an entire bona fide confidence interval. Well, that's the standard error that we derived really pretty rapidly on example 3. Our next goal is just to put all this into practice. So we'll cite these conditions as well as the procedure down below as we work through the problem. But any questions or comments at the moment before we put this to work? Okay, again, one thing that's kind of nice about chapter 19, having done chapter 14 already, is Z star is calculated exactly like this. Typical level of confidences, because humans like nice round numbers, are 90%, 95, and 99%. And so all these values are just ready to go. So that's kind of nice. We'll probably sometimes compute them if we want more decimal places of accuracy. So we're just rounding on the final step, something along those lines. But if you just use this table directly, that would be completely appropriate. I'm not going to be super picky about rounding in the middle. And these are fairly accurate to 4 decimal places, each one of them. So here's a fast problem where the large sample confidence interval is effective. This is some pretty old historical data. And this was a big deal back in the day of 1974, rather, when the whooping cough vaccine was starting to be developed and assessed in large populations. there's a lot of distrust on this, so people were doing studies on the safety and efficacy of the whooping cough vaccine. And here's one particular study. It says, to evaluate the policy of routine vaccination. This became law in Great Britain at this time. Routine vaccination of infants for whooping cough. They monitored adverse reactions in a random sample of 339 infants who received their first injection of the vaccine. So like we do usually, let's start paraphrasing some symbols that we know is useful in the formulas. When it said a random sample, that's good. We have some randomization here. It's involving 339 infants. So that gets us started. And it's 339 infants who received their first injection of this whooping cough vaccine. Now we're being told reactions were noted in 69 of the infants. And that seems to be what this problem is all about. First, let's take a step back. Notice this is absolutely not quantitative data. There's no measurement of, say, what their blood pressure was during their adverse reaction. That might have been quantitative. There's no mention of the age of the infants. There's no any kind of unit whatsoever. There's just these 339 infants either had an adverse reaction or they didn't. That's it. That means these data are categorical. There's exactly two outcomes. The study seems to be focusing on reactions or adverse reactions, if you'd rather say it that way. That means this outcome among the two is considered the success. Sounds kind of morbid in a certain sense. We're saying a success is an infant has an adverse reaction to a whooping cough vaccine. But we call it a success because that's what the study is really trying to make a conclusion about, those that had the adverse reactions. So once we identify the successes, probably another good symbol to put down is X counts the number of successes, and it is 69 in this problem. So that's the start with this. Next thing we'll do, pretty much the same exact process that we took in chapter 17, chapter 18. We'll define the parameters, check conditions, compute the statistic if it's not already done, go for the standard error, and then we'll have an interval. All we'll need next to do is give a practical interpretation. But because the data is quantitative this time, the parameter is not mu. Let's put this down on paper just once more, just for a quick review of this concept. If we're looking into quantitative, data, then the parameter is mu, or there could be several parameters. In chapter 18, there was two of them we considered at the same time. But these data are categorical. So that means the parameter is P. So we should lead off by writing, when we say unknown parameter, we'll begin by saying P equals, not mu this time. If you put in mu right here, that wouldn't lose you credit. I'll probably just put an X there and make a comment. It should be P. But the next thing you say is critical. Here's where we could lose credit. We are creatures of habit, and we just get in the habit when we start off a parameter by saying the following. Let's get down to where we did one. When we're looking into a parameter mu, we say the true average, or the population mean, or the true mean, anything along those lines. But there is no average or mean whatsoever on this problem. So we want to say true proportion. We must say those words. Or you could say percentage. That's just the unit change. You could say true proportion, population's proportion, but you have to say proportion somewhere. You could just even say more briefly, proportion, and then go from there. It's the proportion of the population. This was 339 infants, but we're talking about all infants. So let's begin by saying P equals proportion of all infants. Now, if you read into this, this was a study done in Great Britain, but based on the context, that doesn't really give us a lot. So if you just said all infants, it'll be implied all infants relative to where this study's population was targeted. I'll just say briefly, all infants to indicate the population, not the sample. So proportion of all infants that something happened, we just mentioned the success that had an adverse reaction to, this was specific on first injection. So let's bring that into the parameter. That seems to be pretty important. To the first injection of, this is for a vaccine, specifically the whooping cough vaccine. So let's say that as well, of the whooping cough vaccine. So that's our parameter P this time. When we did this as a chapter 17 problem, we had to say average somewhere. We had to indicate that we're talking about a population, and all is a good way to say that, or we could just say the population average to really emphasize it. Here we said all infants, so we're talking about the population. For the quantitative data, we had to say average of what? What is the unit? What are we really measuring? So on this problem, we said average resting heart rate. But for categorical data, for a parameter P, we don't have a unit whatsoever, so we mentioned the successes. So that's why we said adverse reaction to the first injection of whooping cough vaccine. So those are the parallels going from U to P. It feels a lot different, but we're really not doing anything too fundamentally different. Really, it's just a different kind of data. It's a different way the parameter gets put all together. Well, any questions at all, folks? Comparing and contrasting mu versus P? Okay, and again, that's usually the hard work of statistics. Saying exactly what you're trying to estimate through a confidence interval takes a good amount of time when you're doing this on paper, and it's going to make our conclusion in part F flow really naturally. We're just going to cite what we said P was, and the fact that it's bounded between two different lower bounds and an upper bound. So next step, we're going to check if the conditions are even met. Let's put those conditions here just for a quick reference as a temporary screenshot. So 3 things to check. Really, 1 thing to check very closely, give numbers to, and just 2 things to briefly discuss based on what the problem told us. The problem told us we had a random sample. The method specifically says we need a simple random sample, but this is good enough evidence for us to say at least there was randomization. So we'll put here on condition 1, the sample was selected randomly. We would have to read the study, possibly purchase it to know exactly how they selected the sample. And again, if we're concerned about this, if there seems to be any doubt that this was nowhere near a simple random sample, that the sample is not representative of the population, we'll mention that in the conclusion. But to me, this would be pretty good evidence for us that we're on the right track. We're meeting that condition. Now for condition 2, we're thinking about the large sample. This is pretty blatant that the sample actually is pretty large in some of these problems. At minimum, it's at size 30 to have enough successes and enough failures in the sample, but very often sample sizes have to get pretty large to ensure that, especially if the true parameter is close to 0 or close to a 1. Sample sizes sometimes have to be in the thousands. Here, sample size is pretty large, but that's not good enough evidence. We have to directly say how many successes were there. So in condition 2, the problem straight out told us 69 successes, so we'll write that. There are 69, and this looks funny, but this is just a reminder that that's the benchmark to pass. It's greater than or equal to 15, so we passed that. 69 successes. And notice we didn't use the formula p hat because we don't have p hat yet. We could calculate it if we wanted to use the formula. But if you just have the numeric number of successes, this is a fine way to go. Just state them. So if there's sample size 339, 69 successes, subtract the 2, and you get the number of failures. So that would be altogether 270. Let me write, just as a reminder in the notes, that's definitely greater than or equal to 15 failures in the sample. And so the sample size is large enough. So that means we really can use the large sample confidence interval procedure on this problem. In the next example, we're going to look into what happens when this fails and how the method has to change. But any questions or comments, folks, on getting these counts? Okay, now condition 3. Again, this is one we'll briefly discuss just based on what we know about the problem. A good rule of thumb in order to ensure condition 3 passes, that the population is much larger than the sample, is sometimes called the 10% rule. The population should be at least 10 times greater than the sample size, meaning the sample size is less than 10% of the population size, said differently. If we work the rule of thumb just the exact way the author said, or stated it, it probably looks something like this on paper. The sample size is 339 infants, and this was a study localized in some country, Great Britain. So that tells us that the 339 infants, or let's say it this way, the population is very likely to be more than 10 times as large as N, the sample size, 339 infants. Because we're talking about all infants in the country, there was probably tens of thousands of infants, really, maybe more. But again, you don't have to do research on this. You don't have to look up historical data of exactly what country this really was involved in, what the population was in 1974. Just go based off your gut feeling on the problem, what you know based on what the context is given. And if you have reason to doubt this condition, just say so on paper and then mention it in the conclusion. You might say, after you give the practical conclusion, however, our conclusion may be challenged because we are unsure of the overall population size and the sample was very large. Or you might say our conclusions might be challenged because although the sample is stated to be random, if this was maybe an animal study, you might have a good reason to doubt that simple random sample could even be done, or that the sample is representative of the population. If we feel that way about a problem, we'll mention it in the conclusion. But we did it, folks. Condition checking is usually just a quick discussion, but make sure, once again, just a reminder, show these values in a homework and an exam. I need to know that you know exactly how many successes, how many failures. Any last questions or comments on the condition checking discussion? Okay, flows a lot differently than chapter 17. We're pulling this up just for the sake of quick review and tying the concept together. With quantitative data, we check for randomization. Then, let's see, one of the conditions here we skipped. That was condition number 2, that the parameters are unknown. That's because that's a given in these kind of problems. Then we check robustness by providing a histogram, analyzing how severe the skew is, if there are any outliers, and compare it against the sample size 18 in this problem. But as far as quantitative data goes, it's a little bit more direct. Condition checking, you don't have to produce any graphics. The major thing you're checking is successes and failures, discussing randomization, and the population size relative to the sample. Now, after getting through both parts A and B, that's the context portions, everything else feels like a math problem. We want the sample proportion of successes. When you see that written down on either a homework problem or an exam problem, just write down p hat. That's all it's asking for. So that's the symbol that goes with sample proportion of successes. Computation is not so bad. We just take x divided by sample size n. So this will be the 69 successes from here divided by the sample size, 339 in the problem. And if you'd like, you could approximate this right now. Say go for, I'd say 5 decimal places to 6 decimal places is not a bad idea, because we're eventually getting percentages, really. We want 4 decimal places of good accuracy. So if you round in the middle, 5 or 6 decimal places of accuracy is not a bad idea. But I'll keep this in exact form and just work with that fraction directly in the calculator for the next step. So that's a fast computation. Doing a sample mean definitely takes more effort, and so does a sample standard deviation. We'd probably be using R. But as far as this part goes, standard error of the sample proportion of successes, here's where the formula SE of p hat gets involved. We need to be a little bit more careful with this one. Its formula is square root p hat, 1 minus p hat, divided by sample size n. So here's how I'm going to put this one in the calculator. I'm going to type in directly into any good scientific calculator. I'll use RStudio as a quick demonstration. 69 over 339 multiplied by 1 minus 69 over 339. Divide that whole thing by 339. Because the numerator here is multiplied together, and with a group, we'll include parentheses for carefulness, there's no issue with order of operations divided by 339. So you don't need an extra parenthesis wrapping here around to here, unless there's a plus or minus right where the red dot is in that spot. So let's get our number. This is going to be SQRT if you're using R, 69 over 339 times. In R, you have to put in that strict multiplication. Most graphing calculators, a parenthesis implies multiplication. 1 minus 69 over 339. Divide by 339. And that's our standard error. 0.021868 is what I'll round it to. And let me double check those numbers. 0.21868. Okay, I think we've got it. So now we have standard error. Last thing to do is just put this all together and compute the entire interval. We're going for 95% confidence on this one. And that's kind of nice in a way, because if they say 95% confidence, recall this is not a t-star we're calculating. There's no t distribution in the problem. If you really wanted to, you could scroll up, grab 1.9600 if you want to emphasize the accuracy there. And that's a great way to go. Or you can just put in 0.95 right here for C. We'll probably do that in the next problem and compute it directly if you want more accuracy. So I'll go with the route of just stating Z star here. Z star is 1.9600. So for the entire confidence interval, the formulas above say we're going to compute p hat, the statistic, add or subtract the critical number Z star, multiply that against the standard error of p hat. And again, the parallelism here is really, really striking. In chapter 17, we used RStudio, but in chapter 17, the formulas are essentially the same kind of thing. You start with a statistic, X bar for quantitative data, p hat for categorical with 2 categories. You use a critical number, T star for quantitative, Z star for categorical. You multiply by whatever the formula is for standard error. And it's exactly what we have here, just a different standard error formula. So it's kind of nice to have that strong level of parallelism. Sometimes that can be rare in statistics problems. But for our procedures so far, it's just a direct kind of carryover, just changing the data really. So when we input the values, throw in p hat, 69 over 339, then go plus or minus 1.9600, which came from the confidence level of the problem. Multiply that against the standard error, that figure here by the red dot, 0.021868. And if this was an exam 3 question, just never hurts to remind people, if this is on paper and an exam 3 question, even if we made some weird major slip up on the calculator, our thumb slipped and we wrote an exponent instead of multiplying, I would give this essentially all the credit. You might lose a half a point for miscomputation. Well, next thing we're going to do is just compute the lower bound and the upper bound. This is going to put the parameter in the middle. And here's what the next step will look like. Take 69 over 339, the statistic. I'll start with the lower bound, so minus 1.9600 times 0.021868. So that's our lower bound. Let's carry in 3 or 4 decimal places as appropriate, because remember, it's a proportion, but you could write it as a percent. And if this was a percent, rounding to the nearest 10th or 100th of a percent would be appropriate places to round. So I'll leave it as a proportion on this one and call it 0.1607. So that's the lower bound, and what it's bounding is the parameter all the way on top from part A. P is now in the middle. It's as small as 1.607, and we're going to say it's as large as some value with this specific confidence. It might be smaller, it might be larger than our upper bound, but our method is going to be 95% successful in actually capturing P within our bounds. So same interpretation of what the confidence level is, just like in chapters 14 and 17. And here's our upper bound, 0.2464. So now we've got P constrained in the middle. We defined what the parameter P was extremely carefully to start off the problem by saying what the successes were, indicating the population at the same time, and saying it's either a proportion or a percent. And again, when you do these as homework problems or exam problems, it's a judgment call if you call this a proportion or a percent. But if you do call it a percent, you should come down here and write 16.07%, 24.64%, just to make sure your language here matches up your actual unit down here. Well, that's exciting. That's our first confidence interval for categorical data in the entire semester. Any questions or thoughts at all, folks, getting down to that result here? Okay, well, the next thing we do, let's take another look at chapter 17, just for kind of a quick review of the parallelism here. Once we have the interval, we put a parameter in the middle. Then when we give a practical interpretation, we want one that has no specialized language, that anyone could understand whether they took statistics or not, but it always boils down to the same exact thing. You say what the parameter is, you say the level of confidence in your procedure, read out what the parameter is based on what it was in part A, and just say it's constrained between the 2 bounds you found in the problem. No different at all. Only difference is it's a proportion, not an average. So when we go to finalize a problem, I'll leave P here as a temporary screenshot. We just say these words. We are 95% confident. We must say this part, and we have to use the language confident. We can't say with proportion 0.95 or probability 0.95. Confidence has its own specific meaning, talking about the success rate of the entire top to bottom procedure, starting at identifying the population, gathering the sample, measuring the outcomes, and then finally producing the interval here. So we are 95% confident the procedure is successful, meaning we have to read out one more time the proportion of all infants that have an adverse reaction to the first injection, of if you said this vaccine, I'd say that's okay. It's okay to paraphrase it a little bit. We're specific on what we're talking about, the whooping cough vaccine. But I'll be specific again and just write it out. Of the whooping cough vaccine. Okay, so we're 95% confident. We said what P is. Now we just say is between those two bounds. We already called it a proportion, so we'll leave it in this form, not as a percentage, and say is between 0.1607, meaning as low as 16% of all infants, and 0.2464, meaning as much as almost 25%, 1 in 4 of all infants, had an inverse reaction. Well, that's the final analysis of these data. These are slightly controversial data as well. So when these data were published, it's probably a pretty interesting problem in anthropology on how the population received this information, because this was a routine vaccination policy. Everyone's infant in the right age range had to get the whooping cough injection. And so when this was published, it's probably pretty interesting how everyone took this. Because if you're focusing on the upper bound, that's a pretty large figure there. Well, any last questions or comments, folks, on working through these data? Okay, again, it's pretty old historical data. There's a lot more you could really talk about it, but all we're doing is just giving the honest analysis of the data we saw, and that's the conclusion down there. And by the way, if you ever Google and watch a video on the whooping cough itself, that's kind of a horrifying experience. That's only for people with a really strong stomach. So even though this looks like pretty extreme on the upper end, probably worth it, at least in my opinion. But there's one big problem with our entire procedure, the one that we just ran. Sometimes the things that we're studying are pretty rare, or even just as worse, not even worse, just as worse. Sometimes the things that we study happen nearly 100% of the time. And then we have a challenge. If the value of this parameter is really close to 0, or really close to 1, or 0% to 100%, then to pass condition 2, the sample size sometimes has to be very, very large. But that means even if we had a very, very large sample, it might require a sample size so large that condition 3 is violated, that the population is not 10 times as large as the sample size you're required to take to guarantee at least 15 successes and at least 15 failures. So if P is close to 0 or 1, this procedure, which is called the large sample procedure, has challenges. Sometimes it can't be run at all. So there are other alternatives. And here is the alternative we're going to look into, a +4 estimate for the parameter P. This one's a little bit weird. It's hard to describe exactly what we're doing here. We're literally adding fake data to the sample in a strange way. We're only going to do this if the large sample confidence interval conditions are met. Again, that's when P is very close to 0, 1, putting P hat close to 0, 1. So when that occurs, if we can't use a large sample confidence interval, here's what we're doing instead. We calculate the +4 estimate of P. It's written this way. There's a P here with a little squiggly line above. This is read as P tilde, the name of that squiggly line symbol you see above P. So P tilde is that symbol there. It's a brand new statistic. Its goal is still to estimate the unknown proportion P itself. And here's what we do. We put in the number of successes in the sample, that's X itself, add 2, which means we're adding 2 successes. Then we divide by the sample size, add 4, which means we're also adding 2 failures to the sample. These are not data that we observed, so we're just changing the value of the statistic in this interesting, strange way. And again, it's not always easy to say why. What does this do for us? But we're going to do that. We're going to explain why we would do a +4 estimate, what it helps with, by looking into the brand new procedure down below. So here's the new procedure. The +4 confidence interval for a proportion is going to estimate the true proportion P of successes with a confidence interval. First, we have to have a simple random sample, same condition as before, but there's a major change on condition 2. This is only effective if the confidence level is at least 90%, but that's a normal assumption. It's weird and inappropriate in most contexts to give a 80% confidence interval, for example. 90% is considered to be, in statistical analysis, a lower bound for a confidence interval. But the other condition here is it does not matter how many successes or failures we have in the sample whatsoever. There might be 0 successes and all 10 failures, and that's okay. The sample size itself just has to be at least 10. So that is a massive change. We're going to be punished a little bit for that. Our confidence interval is going to get really wide when we use this procedure, but that's good. If we don't meet the criteria of having at least 15 successes, n times p hat, and at least 15 failures, n times 1 minus p hat in the sample, if this goes wrong, we change the statistic, make the confidence interval wider. So now if we are giving a 95% confidence interval, the statement, we are 95% confident, is likely to be accurate. It's conservative in the sense that the confidence might be even a little bit higher when we go to use a +4 estimator. Well, it changed the procedure just a little bit down here. We put in p tilde, we use the same z star as before, but the standard error is different. Standard error has a change of n+4 in the denominator as well. So to kind of see what's going on here, let's do something we don't do very often in class. Let's pull up Desmos. So the idea is it's all about what's going on inside the standard error. We have a p times a 1 minus p. This is typically a p hat for the ordinary procedure, but I can't put p hat here, so I'm just going to put in p itself. So if we say y equals p times 1 minus p, we get this curve. It's a downward shaped parabola, but it has a specific domain because the statistic, again, that's visualized as a p hat. We can actually fix that. Let's throw in the hat. Okay, there's our hack. We have a statistic p hat. P hat itself is constrained between 0 and 1. Guess we need another hat on that too. So there's our graph. There's not much of a curve there. But notice that p hat times 1 minus p hat, that's where p tilde goes. It has a particular maximum. If p hat is exactly 0.5, then p hat times 1 minus p hat maxes out at 0.25. So if we're looking into data, say p hat is maybe 69 over 339, just like in the last problem, we're at 0.2035. But here's what happens when we go to the +4 estimate. We go +2 here. So that's going to be a 71. We go +4 in the denominator. So we're adding 2 successes, 2 failures. So that's going to be 343 in the denominator. And notice it is bigger. We go from a 0.03 to a 0.07 roughly upon rounding on that one. That doesn't seem like much, but making your statistic a little bit bigger means p hat times 1 minus p hat. It's moving closer to the middle, and so that entire numerator in the standard error becomes larger. This is what's widening out the confidence interval and making a statement with 95% confidence an actual honest statement. So that's the logic of what's going on with the +4 estimate. Any questions at all with what's going on with the brand new formulas? Okay, well, our goal then is to try this out. So the idea once again, is we're just changing the statistic. We're also changing the conditions following a new standard error. So this is the standard error of p tilde itself. But really, our analysis should feel very familiar to what we did before, even when we're using the +4 estimate. So here's our brand new context to give this one a try in. After we get through this problem, probably once we get back from spring break, we'll turn over to hypothesis tests procedures, and then move into chapter 20, handling more than one population proportion. So here's our new context to digest. Example 5 says the technology underlying hip replacements has changed. Operations have become more popular. We're told there's over 250 done in the United States in the year 2008. So this gives us an idea of the size of hip replacements being done. But here's the next drama in the problem. We're told that starting in the year 2003, highly durable ceramic hips were marketed. So it sounds great, they're durable. You wouldn't want a total hip replacement being done and something goes wrong with it. That would be traumatic. But it says next, unfortunately, for too many patients, however many that is, we're going to estimate that, the increased durability has been counterbalanced, that sounds like a pun, by an increased incidence of squeaking. So again, this sounds kind of funny in a way, but you have to imagine if this happened to you, this is like having tinnitus, ringing that never goes away in your ears. You just went through a hip replacement, which again, that's an extreme and brutal procedure. And then during your recovery, your hip begins squeaking, and that could slowly drive you insane. So these are very, very unhappy customers, probably more likely than not. And this was being investigated. In the May 11th, 2008 issue of New York Times, reported that in one study, 143 individuals who received ceramic hips between those years, again, 2003, 2005, 10 of the hips developed squeaking. I don't know how they got to the 143 individuals. Nothing's stated here, and you don't have to look up the study and read it. You might get more information, but that's never required for a homework problem or exam problem. We'll work off the context that we see here on paper. Here's what we know so far. The sample size is indicated 143. And we have a notion of what the successes are going to be. It's receiving the ceramic hips that developed squeaking. So again, a success is once more not a good thing, but it's the thing the study is focusing on. So we'll say here, these are the successes, which means the number of successes in the sample, X, is 10. So that's the whole write-up of the problem so far. And question A asks us directly, or part A rather, explain why the large sample confidence interval, the conditions rather, for the large sample confidence interval are not met. There's a lot of ways to answer this, and one way you could say is there's no indication of a random sample. That is important, so let's mention it here. No indication. The sample was random. So that's potentially pretty problematic. If it wasn't a random sample, sometimes authors of these studies argue differently, that 143 is representative of everyone who had the ceramic hip replacement between 2003, 2005. So that's a problem right there already for the large sample confidence interval procedure. But the other problem is, when we say large sample, we're talking about the number of successes and failures in the sample. This one has a lot of failures, 133, but only 10 successes. So that's the big reason we're rejecting this entire method. There are only 10, which is less than 15. That's our benchmark for passing the condition here. Successes in the sample. And so the conditions are not met. If we use only 10 successes in the sample, our entire procedure, when we go to say with whatever level of confidence we select, with 99% confidence, for example, we have this estimate, that's not likely to be honest anymore. The true confidence is probably lower, and it could be remarkably lower, maybe 97, 96%, and we're stating 99. So not having a pass right here on the number of successes means we shouldn't even use a large sample confidence interval procedure at all whatsoever. But that doesn't mean we give up. We're going to instead use the +4 interval to to estimate the proportion with the confidence interval. On this one, we're providing a top to bottom complete analysis, not too different with what we did in example 4 with parts A through F, but this one is just really our author's so-called 4-step method of a statistical analysis. We'll state what the practical question is, define the parameter, check conditions, compute the interval, and give a practical interpretation. Before we jump in, any questions at all with part A or any of the context? Okay, well, let's get started then. First thing we want to do, just to kind of orient ourselves to see if we really understand the context, is state what the practical question is that requires some inferential procedure. There's no question mark whatsoever in this kind of problem, but that's okay. This is an estimation problem, so the practical question would be, what is an estimate for the true, you could say proportion or percentage. I'll go with percentage in this problem just to vary the way we can write this out. I'll say the true percentage of these hips that squeak. So that's kind of the essence of our problem. We said, well, they said in the study, 10 out of the 143 developed squeaking. Well, we want to know the true percentage in the entire population of these hips that squeak. So that's a practical question. Notice this isn't completely nailed down. We didn't say what kind of hips, when the procedure was done, exactly what the population was. But we'll definitely do that when we define the unknown parameter. We have to define this one really carefully, and that's our next step. Because the data is categorical, we begin by saying P. If I said true percentage here, you can change that up. You could say population proportion, population percentage, but I'll parallel that language. P is going to be equal to the true percentage of all. We want to mention what is the population. It would be not the 143 people with the hip replacements. It's everyone that had those hip replacements. So I'll say all people with a ceramic hip, implying that they had a total hip replacement. So they've already been through hell really to get that done, but they did it. They're all people with a ceramic hip. And really that's not quite good enough. Medical data is really kind of touchy because medical data parameters like this P we're defining is a moving target. Medical technology, even if the underlying component, the ceramic hip, the medical technology changes year after year. They get better at installing these. The way they install them, the technology, the training evolves over time. This problem is anchored between 2003, 2005, so we should really mention that. So let's say all people with ceramic hips installed. I don't know if that's the friendliest word. That doesn't sound patient-oriented, but it's just a brief way of saying it. Installed between 2003 and 2005. So we're saying it's a percentage because the data is categorical with two outcomes, successes and failures. When we said all people with the ceramic hips installed between those years, we're mentioning the population. And we have to loop in what the successes are. So we'll just say here that develop squeaking. Again, the first time I read this problem, it sounded slightly humorous, but the more you think about this, it's a very, very serious statistical problem. These people are likely, I bet you, plenty of them, the suing type. And so this is probably a problem that led to litigations occurring. A lot of serious stuff would have happened after the conclusion of this kind of study. Well, the next thing we're going to do is check for conditions. But any questions at all, folks, nailing down that parameter? Okay, well, that's our second run of putting down a categorical data parameter in a statistical inference procedure. It'll get easier and easier the more we practice it. But the next thing we're checking is now the conditions altogether. And it's not too bad, except there's something kind of missing here. Once again, no indication that the sample is random. We'll just duplicate that statement. There's no indication the sample is random. This doesn't mean we're going to stop our statistical analysis right here. We're going to keep on pushing forward, but this is a pretty big shortcoming. So we're going to mention this in our conclusion. So we'll come back to that shortcoming there. Next thing, I forgot to do one part in the planning phase. Confidence has to be at least 90%, but we never did this. Some of the problems are a little bit open in the sense that you can choose whichever confidence interval you prefer, confidence level rather. We never stated one, so let's put one down on paper here. I'll choose this one. Let's say it's a serious problem. Let's go for a high level of confidence to match the seriousness of the problem. Let C be 99%. So we're going to estimate squeaking hips proportion, rather percentage as we said it, with that level of confidence, high degree. That means we passed condition 2, but again, we would assuredly always pass that portion right there on the confidence level. But we fully passed condition 2 because the sample size is definitely over 10. So we'll say here, confidence is 99%, which is definitely greater than or equal to 90%, and N equals, I forget, let me double check, 143 hips that were installed. So N is 143, which is greater than or equal to 10. So this condition is met. So we're off to a good start, other than the most important condition, randomization, being an open question. The next thing we're going to look into is we have a problem with our entire normal distribution itself if we take a sample that's way too large. The population has to be a lot larger. It should be at least 10 times greater than the sample size. So when we see 143, in certain medical procedures, that could be a problem, especially if this is experimental technology, like if we're doing some kind of interesting exoskeletons for a random example there, and maybe only 150 have been done. We take a sample size 143, we need a whole different method. Normal distribution would not apply. But if we scroll up through the problem, it said at one point that operations have become popular for these hip replacements. This is not the right year. Our target years are between 2003 and 2005. But in 2008, there was 250,000 hip replacements. That's probably enough to give us a good indication that between these two target years, this is probably not that large relative to the population. It's very conceivable that the population is more than 10 times this size. So we'll say here, it is reasonable to assume the size of the population is more than, when it says 10 times the sample, we mean 1430. So probably more than 1,430 ceramic hips were replaced between the years of 2003, 2005. Again, if you have doubt on that and you say that's probably not feasible, that'd be all right as well. And then we'll just mention this shortcoming in the conclusion as well. So support your answer based on the information you see in the context. If you want to go above and beyond, you can research this problem. That's probably going to be a lot of research, but you're never meant to do that. To figure out exactly how many ceramic hips were installed between 2003, 2005, that's going beyond the scope of the course. That's a great research question, but you never have to work that hard. Well, we did it, folks. That's the rundown of the conditions. Next is the computations, but any questions whatsoever with this stage here? Okay, so it says for step 2, carry out the necessary computations. That means we have to compute a couple things here. If we're going for 99% confidence, we can scroll up, go to our table, and find the critical number Z star. But it's just as easy to compute it from scratch. It goes Q norm. In chapter 17, you would have been using QT. We put in a particular fraction, 1 minus the confidence level as a decimal, divide by 2. No degrees of freedom in this problem, so we changed that step from chapter 17, 18. Well, lower dot tail equals false. And that's our critical number. Once again, the syntax is above example number 3 in the notes. Or below example 3 in the notes. We already have this number. Let's just place it down, maybe with a little bit more accuracy. 2.57583. And as usual, let me double check my digits here. You think it'd be easy to memorize 6 digits, but that's a challenge for me some days. So that's our critical number that corresponds to 99% confidence. So that's one thing down. We still have 2 other things we have to calculate. We never computed the statistic. Not T, let me change that, sorry, P tilde. It's not P hat this time. The way this one's computed is we take the number of successes in the sample, which is X, add 2, then we divide by the sample size N, add 4. Effectively, we've added 2 successes, 2 failures into the sample altogether. We're just trying to widen out our confidence interval even more, so 99% confidence as a statement becomes more accurate. So once we calculate that, the next thing we have to compute is standard error. Not of p hat, we've changed the statistics, so we've changed the standard error as well. The formula for this is going to be p tilde times 1 minus p tilde, divide by, here's where a common mistake is made. It's not n any longer, it's going to be divided by n plus 4 again. So watch for that little computational thing right down below here. Once we do those 2 left computations, we'll just put the whole confidence interval together, just like we did in the prior example. We'll grab a parameter, write down a conclusion, which probably feels a little bit mechanical and standard based on every single confidence interval we've done to date. So this is just the next part of the math problem side. Well, we're just about there, and I bet you if we really worked down to the minute, we could get this down on paper. But I propose, because again, we have spring break coming up, we're going to be on vacation the entire next week. This is probably a pretty good stopping point for us, so that when we return on the 30th, we can refresh this, how it goes, attack these formulas from scratch a little bit fresher, and then I think that'll be a better way to tie up the problem, rather than racing through the computations. So we'll call it a day right here, so we're not working down to the minute on the last day before a week-long break. It feels kind of cruel and unusual. We'll turn it over to the class at this point. Any last questions or comments at all, folks, before we call it a day? Okay, well, have a great weekend, folks. Try not to work too hard, but if you're getting caught up, if you have any questions, I will be available by email. I'll be checking it in the morning each day over the break. But otherwise, we'll be back to this spot here, finishing off this squeaking hips problem on the 30th. Take care, folks.